All right, everyone, welcome back to 217, the online edition. I hope you all enjoyed your break as best you could. And I know doesn't quite make up for having in-class meetings, but I'll do my best with this. Try not to swear too much when I get frustrated. All right, so let's pick up where we left off. So before break, we had been talking about simple linear regression models. So that's what we're going to pick up now. See if I can minimize that thing. Yep, okay. All right, so let's see. Let's blow that up a little. All right, so we talked about simple linear regression before we went on break. We talked about the assumptions that we needed to not violate in order to run a simple linear regression. And we looked at how we can estimate the model using R and the two key components of our models, the intercept and the slope. So now we're going to continue on with inference about intercept and slope. All right, so just to let you know or remind you that as we are working through these notes, you are more than welcome to pause or, sorry, I'm fiddling with the screen trying to make sure it's doing what I want it to do. You can always pause. Why is it being like this? All right, this would be a pain in the butt. Damn it. That's super annoying. Okay, well, I'm gonna have to mess with this, I guess. But you can always pause the recording as needed, or I think you can actually speed it up too if you want. So just a reminder, that's an option as well. And these notes should take about a half an hour to run through. I think we have 7 pages. All right, so let's get going on these. All right, now. Let's see, we're working on day 26. So we're going to be focusing on, like I said, inference, dealing with slope and intercept. So we're actually going to be looking specifically at hypothesis testing for slope and then confidence intervals for both slope and intercept. And we're going to start with the parametric approach. But these are a bit spaced out here and there. So there we go. Okay. All right, I'm going to blow this thing up a little bit because my handwriting is kind of small. Rotate the screen as well. Apologies if, oh, sorry. I'll make it extra weird. Rotate around. Okay, there we go. Try and get myself as much room as I can to write. All right, so starting with confidence intervals. So let's see, confidence intervals for intercept and slope. So the general form is the same for this as it is for any confidence interval. So we're going to have our estimate plus or minus some multiplier times the standard error associated with our estimate. All right, so why is this being like this? Oh my gosh. Hang on. Technology is fighting me. What the heck? Sorry. Oh, there we go. Okay. All right. Now, hopefully this gets better. All right. Now, we're going to start with looking at confidence interval for the y-intercept. So remember, confidence intervals are giving us a range of plausible values for the true value of our parameter of interest. In this case, y-intercept, notationally, that's beta naught. So writing this out, the form for this is going to be b naught plus or minus, be a little bit more specifically about it, our t star multiplier, where that's coming from a t distribution with n minus 2 degrees of freedom, multiplied by the standard error of our estimate for the intercept. So b naught, as a reminder, this is our estimate for the y-intercept. This is where we're getting our multiplier. And that's just our placeholder for the standard error. All right. Why can't I scroll on this freaking thing? There we go. All right. Now, interpreting our confidence interval. So remember that the intercept, that's where x equals 0. So our generic interpretation. So for an x value of 0, we're whatever percent confident that the true mean value of y is going to be between our lower bound and our upper bound in units of y. Hypotheses, we don't really care about doing a hypothesis test for the y-intercept because we've already talked about this. The y-intercept is generally winds up being an extrapolation, and most of the time it's a completely illogical thing anyway, so we don't even care about doing a hypothesis test for it. Slope, though, on the other hand, that's a little bit more interesting. It's got a little bit more stuff going on. So let's see. The confidence interval for our true slope value, or beta 1, is calculated as B1 plus or minus, again, our t-star multiplier with n minus 2 degrees of freedom times the standard error of our slope estimate. So B1 is our estimated slope. T-star multiplier we've already talked about, and this is our standard error associated with our slope coefficient. Okay, now our interpretation. Sorry, I don't know why the screen jumped quite that badly. Remember that slope is referring to a rate of change, so how much we estimate the response is going to change when we change x by 1 unit. So that's reflected in this interpretation. So for a 1 unit increase in x, we are whatever percent confident that the true change, that part's important, in the mean value of y is going to be between our lower bound and our upper bound in units of y. Hypothesis testing, we can do a hypothesis test for slope, and that is meaningful to us. So in notation, we would write that as the null hypothesis is that beta 1 is equal to 0. In words down here, we'd say that there's no linear relationship between x and y in the population. The alternative is going to be that beta 1 is not equal to 0, or that there is some relationship. All right, now, one thing I want to point out here is that we can definitely do a one-sided test for the slope coefficient. We can test to see if that relationship is negative. We can test to see if that relationship is positive, in addition to just testing to see if there is a relationship in the first place. All right. Now, moving on, let's look at how we can actually conduct these hypothesis tests. So we're going to start with the parametric approach. So we can calculate our test statistic by hand, or we can snag information from the output. So if we wanted to conduct this by hand, now our test statistic, we're going to be using the t-distribution, and in the context of the simple linear regression, we have n minus 2 degrees of freedom. So that's where we have this t-distribution with n minus 2 degrees of freedom. All right, to calculate this by hand, it's actually a fairly easy formula. T is equal to our estimate for slope divided by the standard error around that estimate. That's it. And these values we're going to pull from our output for the summary output for the linear model. All right, so let's run through this in the context of an example. So our data set for this, we're going to be looking at plant diversity for 22 islands off the northeastern coast of the U.S. Actually, I've seen this data set before, and I've actually been to one of these islands, so it's kind of neat. It's a research island off the coast of New Hampshire called Appledore Island. It's not generally open to the public because it is a tiny island for starters, and it's just there for research. They do a lot of research on songbirds, which is pretty interesting. Sorry, side note. All right, so we're going to be looking at 22 islands off the coast of New England, basically. And what we're looking at specifically is we want to see if there's a relationship between the number of available soil types and the total richness of plant species, which is really just referring to the number of plant species on the island. So here's our two variables, total richness, that's going to be our response. And then soil types, that's going to be our predictor. So we're going to fit a simple linear regression model. So using that LM code, which we've seen before. And we have total richness, which is our y variable, by our x variable. And then we're going to run the summary on that linear object and check out some output. All right, so again, we've seen this before. Change the ink color. All right, So just as a quick review, this is a real good spot to take a pause and write out your linear model. I'm going to assume that you paused to write out your linear model. And so what we should have is total richness with a hat on it is equal to the intercept 143,910 plus our slope coefficient 14.153 times our predictor of soil types. That would be our linear model for this. All right, now let's calculate our test statistic. So let's see. I'm just going to put a little note here just to indicate where I'm snagging values from. All right, our parametric test statistic, as we wrote down above, it is the slope estimate divided by the standard error around that estimate. So here's our B1 value up there, so 14.153. And then we're going to divide it by our standard error for that estimate. It's a B. Jeez, I just made it worse. Standard error B1. All right, close enough. Okay, so that value 2.362. When we math that out, we should get 5.991, which, surprise, matches that. So cool, we did our math right. And from that test statistic, we would get a p-value of less than 0.001. All right, now if we wanted to calculate the confidence interval for this by hand, quote unquote, we're going to use this QT function. So just as a reminder, since it's been a little bit since we've seen this or talked about this, that what we're doing when we're getting these confidence intervals is we are specifying the cutoffs that we want. So this 0.975, that's referring to this cutoff over here. Remember, R is reading this from left to right. This cutoff would represent 0.025. And so what that's saying is that in each tail, there is 0.025% of our distribution. 25, there we go. Which means that there's a total of 5% of our distribution in the tails, leaving 95% of our distribution between those two cutoffs. So we're specifying that we want to get the multiplier that'll give us these cutoffs, which is what we get right here. And we had started with 22 islands. So n minus 2, that's where we're getting that degrees of freedom equals 20. So this part here, this is what's getting us that 95% confidence interval. We could always use this to calculate some other level of confidence if we wanted to. We would just have to change that value. All right, now here's the by hand part. Now, here's our code for this. And what we're really doing is we're really just using R as a calculator for this. So let's look at the components that we have here. There's our B1, our estimate for the slope. This piece here, this C parenthesis, -1, +1, this is really doing that plus minus action. Here, this is getting us our multiplier. This is just that same line of code that was above. And there is our standard error estimate from our summary output. So you run this line of code. Here's what it spits out just below. So that means that we have a confidence interval of 9.225 up to 19.080. All right. Now, we can also just tell R to do this for us. Like, we do need to know how to do this by hand. That part's important. So I'm going to put a star next to this, because don't be surprised if we ask you to do something like that once in a while on homework. So we can just have R calculate this directly. Now, as a reminder, this confidence function here, this is the parametric method. So this is completely fine to use if you have no violations of your assumptions. And we've seen this bit of code before, so this is nothing really too new. But as a reminder, first line is spitting out the confidence interval for the intercept. And the second line is giving us the confidence interval for the slope. Sorry, that came out weird. There we go. All right, so let's look at how we interpret these. All right, interpreting the confidence interval for the y-intercept. Again, the y-intercept, that's where our explanatory variable is equal to 0. So for an island with 0 soil types, we are 95% confident that the true mean number of species is between the lower bound and the upper bound. So in this case, 7.388 to 280.432. Nice narrow interval. Great. Oh, forgot my units of measurement. Species. All right. Now, looking at the slope, again, slope is referring to change. So when we increase x by 1, we're talking about the change in the response. So for each additional soil type, we are 95% confident that the true change. So instead of saying change, I'm going to be a little bit more specific because my interval is entirely positive. I'm going to say the true increase in mean number of species is between 9.225 to 19.082 species. All right. Now let's look at a plot real fast. So as term plots, we've seen term plots before. It's just been a little while. So we saw them in the context of the ANOVA setting. Now remember, when we were working with ANOVAs, we were still fitting a linear object. So that's why we were still able to use term plots. Now, are smart enough that when we feed in a linear model or a linear object that has a quantitative predictor and a quantitative response, it recognizes that you really want to see a term plot regarding a regression line. So that's what we have here. So R knew that we wanted to see a line. So what we're looking at with this plot is that this plot is displaying the linear regression line, or our estimated line, and that's the darker blue line through the middle here, so that line, and then the lighter blue around that is the 95% confidence interval band for the true mean number of species at each value, or each number of soil type. So if we were able to see a scatter plot of this data, we would likely see that this section here is where the highest density of points was, because we can see that we have more precise estimates, or a more precise interval around the center here, and then our confidence interval band is getting wider towards the ends, so over here and over here. And that's tends to be where we would see fewer points. We have less data, therefore we have a little bit more variability, slightly higher error. All right. Now, let's talk about the nonparametric approach. So we would want to use the nonparametric approach in a simple linear regression setting when the normality of the residuals, fix that, we would say is compromised. So this could be something like, sorry, write that a tiny bit neater. So this could be an issue of skew, or perhaps we have very heavy tails, something like that. Could be considered problematic in terms of the assumptions. So that's when we would say this is compromised. And so this is sort of a two-pronged thing. One is that we would use the nonparametric setting when we have issues with our normality assumption. And the other piece that's important is that there needs to be no influential points. So as long as we have no influential points, we can get around the issues with normality by using this nonparametric approach or the permutation test. All right, and we would check this, we would check the normality and the influential points using the diagnostic plots that we looked at before we went on break. All right, so to do this permutation test, we've done this before, so this is nothing really new. What we're going to do is we're going to shuffle the explanatory variable, and then we're going to compare the original slope, or the observed slope from our original data, to our simulated slope from the permutations. Now, how this really works, if you were trying to sort of think about what was happening, is if you think about your data set as being made up of a whole bunch of ordered pairs, where each pair has an X value, each pair has a Y value. So under the null hypothesis, there's no relationship between X and Y. So if there's no relationship there, it shouldn't matter which X values go with which Y values. So what we do is we hold the response values constant, and then we shuffle around the X values and sort of reassign them to Y values, and then we recalculate our regression line. And that's where we're getting our permuted slope values from. So we do that a whole bunch. So looking at the code here, what we have is our T-obs. There's our linear model. Remember that this $sign, coef, and then 2 in brackets. This is just telling R that we want to only pull the slope coefficient. So being very specific about that. And then our T-obs, yep, that's our original observed slope. So we're good there. Now this next chunk of code, again, we've seen this before. So this first piece here, this is getting our permutations. So our permutation loop. Now remember, with the permutations, we're shuffling. So we're shuffling our X values, holding those Y values constant. And then this chunk here, this is just plot code. So the first 2 lines get us the plot on the right, or apologies, first 2 lines get us the plot on the left. Oh, that's about. Then the second 2 lines are getting us the plot on the right. And these red lines are marking out where our observed slope was. And because it's a 2-sided test, we're looking at both the positive and negative values. And then we can tell all right, calculate our p-value for us. And our permuted p-value from this, it's super tiny. All right. Now, again, we've done these permutations before. There's really nothing new going on here. Now, let's get a little bit of review in because it's been a while since we've talked about all of this stuff. So, interpreting the p-value. Remember that the p-value interpretation, it has 4 components. It has the probability of your same results or more extreme. If the null is true. You put each of these components into the context of the problem and your interpretation builds itself. So probability, we have a super tiny p-value. So we're going to say there is less than a 1 in 1,000 chance of seeing a slope as or more extreme than 14.153 if there really is no linear relationship, and then context between, how did I say this? The number of soil types and the number of species. All right. Now, the conclusion. So as a reminder, the conclusion, this is where we are going to evaluate the p-value using our hypotheses. So first part of the conclusion is about the null. So, extra stuff down. We would say that we have very strong evidence against there being no linear relationship between the number of soil types and the total richness. Going back to the original variable name, spicing it up. And then we need support. So beta 1 equals 14.153. And that's coming from a permutation test p-value of less than 0.001. So we can conclude there is a linear relationship between these variables. All right. Now, confidence interval with the nonparametric approach. Reminder, we're referring to that as bootstrapping. So we can bootstrap a confidence interval, and it's under the same, like we would want to do this when we have the same problems that would lead us to use a nonparametric hypothesis test in the first place. So this is useful when normality of residuals is compromised. And it works as long as there are no influential points. All right, so as a reminder, when we're bootstrapping, we are going to resample the original data with replacement. And then we're going to calculate the 2.5% and 97.5% quantile. So if it helps to sort of think about what that is, you could scroll back up to the previous, page or two. I think it's the bottom of page 3 where I sketched out that little distribution. All right, so code-wise, we're just assigning t-obs in this line here. And then we have our bootstrapping loop. That is all of this. Nope. Yep. So bootstrapping loop. Now, when we had the permutation loop before, it was we were shuffling our x values. So we had our y value by our shuffled x values. Here, to do the bootstrapping, we still have our y by x, but then in our data call, we're going to use this resample line. So that's what's getting us our bootstrap. And then this bit here, this is assigning our quantiles or pulling out our quantiles from our permuted values. So this is where we're getting our confidence interval. So here's our CI code. And then it spits out this output. We've seen this before. So we want to snag that chunk right there. And that is our 95% confidence. Oh, no, 95% bootstrap confidence interval for the true value of the slope beta 1. All right. Now, let's see, last bit here, almost done. We're just going to look at some plots of our permuted values here, our permuted slope values. So this looks kind of similar to what we looked at for the hypothesis test for the nonparametric approach, but there's a few things that are different here. So the red line here, this is our observed slope value. And then these lines here, these are referring to the upper bound and the lower bound of our confidence interval. So these are marking off our percentiles. So this would be our 0.975 cutoff. This would be our 0.025 cutoff. All right, so 95% of our permuted distribution lies within these lines. And the remaining 5% is split in half between the left tail and the right tail. And then the plot over here on the right, let's see, this chunk here, this is giving us the right-hand plot. This first chunk, this is just giving us the left-hand plot. So the plot on the right is showing us basically the exact same thing as the plot on the left, only we've plotted it as a density curve as opposed to a histogram. Now, let me just jot down comments that I made before. So the blue lines are at the upper bound and lower bound for the confidence interval. Those are the confidence interval bounds. So the percentiles, there you go. And then you notice that I'm skipping over the interpretations, and that's just because the interpretations for the confidence interval are the same regardless of which method you use. All right, so that wraps up our day 26 notes, talking about how we can do hypothesis testing in the context of a simple linear regression. So hypothesis testing for slope, looking at both the parametric and non-parametric approaches, and then confidence intervals, again, parametric and non-parametric for the slope and for the intercept as well, and then how we would interpret those. Again, you can always rewatch this video as much as you want. I will post the nice looking version of these notes in D2L as well. And otherwise, have a great rest of your day. And don't forget to check in during our class time on Monday. So either 11 o'clock if you meet in Linfield, or 1:10. Yeah, that sounds right. 1:10 if you meet over in Roberts. Bare minimum, even if you don't have questions, please just check in briefly so I know that you're still alive and are participating in this class. Otherwise, have a great night, and I'll talk to you guys later.